Today we need to refresh our memories on the concept of enthalpy. Enthalpy is the heat lost or gained from the system during a chemical reaction. If energy is given off by the system to the surroundings, we recall that as exothermic, and if heat is taken in from the surroundings to the system, that is endothermic. So I would like you to read your notes and join me again when we get to the concept of spontaneity, which is right about here. Spontaneity in chemistry is not the same as spontaneity in general use. Spontaneity in general use means you're up for anything at any time. Spontaneity in chemistry means that a reaction happens without any outside intervention. The people at College Board like to hear from you, instead of the word spontaneity, thermodynamically favored. If a reaction in the forward direction is thermodynamically favored, it happens on its own. It just happens. If it is thermodynamically not favored, energy must be added to overcome the deficit. Let us recall that the spontaneity does not tell the rate of reaction. The rate of reaction is governed by the concept of kinetics. Kinetics and spontaneity are not the same thing. All right. So if a reaction is spontaneous in the forward reaction, that means it is non-spontaneous in the reverse reaction, so it is irreversible, and it will only proceed in one direction. A reversible reaction will proceed back and forth between the two end conditions, and a reversible process is at equilibrium. When a reversible process is at equilibrium, there is no change in the free energy. Okay. Now we do recall exothermic is spontaneous in the forward direction, and endothermic is spontaneous in the reverse reaction. I'd like to say a few words about the calculation of enthalpy. We in chapter 5 went over many different ways to calculate enthalpy. Let's review them quickly. The bond energy of a reaction can help you figure out the enthalpy of the reaction. Enthalpy is delta H of the reaction. Bond energy would have you determine the amount of energy that is stored in the bonds of the reactants and then the bonds in the products. So in this case, if this were to be broken apart, you would need to input energy to break up the bonds that are existing between the carbon and the hydrogen, and then there would be energy released when the two hydrogen bonds formed for the H2 gas. This is the only oddball in all of these that we will talk about, and you take the bond energies of the reactants and subtract the bond energy of the product. In every other case that we will talk about, it is the opposite. This is the oddball. Got that out of the way quickly. Another way to calculate the enthalpy of a reaction is the enthalpy of formation. You can find in chemistry data in a chart something that looks like this. This is the enthalpy of formation of a compound. Let's say the enthalpy of formation for water in its liquid state. That's the amount of energy that was gained or lost when two hydrogens formed a bond with an oxygen. This little ought sign denotes standard conditions, which is not STP. Standard conditions, 25 degrees C, what atmosphere of pressure, and if it is appropriate, it would have a concentration of 1 molar. I believe off the top of my head that the energy of formation for liquid water is 286 kilojoules per 1 mole of water. If I'm wrong, so sorry. That means 286 kilojoules of energy are released when water is formed from its elements. By definition, the enthalpy change of the formation of an element is 0 kilojoules. We're kind of thinking that it was here before we got here, so we don't have to worry about the energy exchange that caused the elements to form. We can also use Hess's law, and you will remember that Hess's law is a puzzle for smart kids. You have elementary reactions that can be used to figure out a target reaction. And you will have to first determine whether you need to reverse a elementary reaction. If you reverse the reaction, you have to reverse the sign of delta H, and then once you have got your elementary reactions running the way you want, so they add up to the target reaction, then you have to make sure that you multiply each reaction. And remember, you can multiply by a decimal if you need to reduce the coefficients of the target reaction. And if you multiply the reaction, you must also multiply delta H before adding up the elementary reactions to find the enthalpy change of the target reaction. You can also read the enthalpy change from a graph. So if I had a graph that looked like this, and these were the reactants and these were the products, this is the potential energy of the reactants, the potential energy of the products, and this is time. All I would do is subtract the products minus the reactants, and that would give me delta H. This is an exothermic reaction, so the sign of the products having a lower potential energy than the reactants would always give me a negative delta H value. If, on the other hand, I have an endothermic reaction, where this is the products and this is the reactants, this is time going forward, I would still subtract the products minus the reactants, only this time delta H would be a positive number. I can also, if I am at constant pressure, figure out the enthalpy of a reaction by remembering that the heat lost or gained at constant pressure is equal to Q. So at constant pressure, Q is equal to MCAT, where M is the mass, C is the specific heat, and that would be in joules per gram per degree C. And T is delta temperature, where it's the final minus the initial. Please recall that M can stand for moles, and if it stands for if you put moles into MCAT, then your value for the specific heat is going to be joules per mole per degree C. And I can also, the last way I can find my enthalpy is to look on some thermodynamic charts and recall that the enthalpy change of a reaction is equal to the sum of the enthalpies of the products minus the sum of the enthalpy changes of the reactants. Please recall that all of the enthalpy values that are listed on a chart are for 1 mole of each one of the species. So if you have 2 moles of water, you take that negative 286 and multiply it by 2.